After more than 4 billion years, Earth has gone through 3 eons. There was early life, but it was scarce and insignificant. The planet will always change, and life will adapt to those changes in one way or another. With the end of the Proterozoic Eon, the appearance of more advanced organisms marked the beginning of a new eon. An eon of life, the Phanerozoic Eon. To signal the start of the eon we live in, a great event occurred, the Cambrian explosion of life. Hello, passengers, and welcome back to the Time Machine. I'm Driver, and today we'll continue our journey from the past to the present, exploring Earth's periods through the video, the Ordovician Period. Now, let's get started. The Cambrian explosion is one of the most important events in the history of animal evolution. This event occurred around 541 million years ago and lasted for about 20 to 25 million years. During this time, the number and diversity of animal species increased suddenly, and many groups of organisms with fundamental characteristics, along with many modern species, originated from this explosion of life. Before the Cambrian explosion, most living organisms on Earth were single-celled or very simple multicellular organisms. After this explosion, most complex body forms appeared, from vertebrates to invertebrates like arthropods and protozoa. The cause of this explosion is thought to be environmental changes, such as an increase in oxygen levels in the oceans and atmosphere, the evolution of new species, including the development of genes controlling growth, or the emergence of new food relationships, which increased evolutionary pressure. Whatever the cause, the Cambrian explosion of species remains one of the major turning points in biological development and has shaped the diversity of life on Earth for hundreds of millions of years thereafter. Unlike the first 3 eons, in the Phanerozoic Eon, eras and periods are divided much more densely. The reason for this is the sudden and continuous environmental changes on Earth, which occurred more frequently and caused mass extinctions previously unseen. The Phanerozoic Eon began with the Cambrian explosion of life. This explosion was ended by a minor extinction event, marking the end of the Cambrian period around 485 million years ago, and ushering in a new period, the Ordovician Period. The Ordovician Period is named after the Ordovices, a tribe that once lived in the area that is now Wales. The name was proposed by Charles Lapworth in 1879 to resolve disputes between followers of Adam Sedgwick and Roderick Murchison, who had classified the same rock layers in northern Wales into the Cambrian and Silurian periods. Lapworth recognized that the animal fossils in the disputed strata were distinctly different from fossils found in Cambrian or Silurian strata and suggested that they be classified into a period of their own. The first geological era of the Phanerozoic Eon is the Paleozoic era, which lasted from the beginning of the Cambrian period to the end of the Permian period. A key feature of the Paleozoic era was Earth's high sea levels. For most of this era, the majority of the continents were submerged underwater, leading to frequent flooding. At that time, much of the North American continent was covered by water, which helped preserve many Precambrian fossils under these waterlogged layers of sediment until today. During the Ordovician period, tectonic plate movements caused the continents to merge into a supercontinent known as Gondwana. This supercontinent was formed from the land masses of Africa, South America, Australia, and Antarctica after merging into a single landmass. This new supercontinent gradually drifted southward throughout the Ordovician period until it reached the South Pole. At the same time, the landmass that would later become North America also began to form and combined with other land fragments to create the continent of Laurentia. This continent was located at the equator and was separated from Gondwana by a small ocean called the Iapetus Ocean. Initially, the climate fluctuated between warm conditions and periodic cold spells. The average air temperature at the equator at this time was about 48 degrees Celsius, and the ocean temperature was 45 degrees Celsius. The high levels of carbon dioxide at the time may have been responsible for these elevated temperatures. This could have delayed the diversification of life forms at the start of the Ordovician period. However, as the continents were concentrated in the southern hemisphere, massive ice sheets began to form, which helped to significantly lower the planet's temperature. During the Ordovician period, most life existed underwater, primarily in marine environments. Although not as abundant as during the Cambrian explosion, marine life in the Ordovician period increased fourfold. The organisms living during this time included brachiopods, corals, bryozoans, gastropods, and non-vascular plants like mosses, which began to appear. Squid-like creatures were the primary predators of this period. Their modern relatives are squid and octopuses. One of the most common species was Orthoceras, a strange creature with legs growing from its head. There were also brachiopods with bilaterally symmetrical shells. Other invertebrates living in Ordovician waters included sponges, corals, and the first fish species. The fish of this period were small and jawless, known as agnatha, or jawless fish. They fed on organic matter from the ocean floor by sucking and filtering. They had small protective shells on the front part of their bodies. An example of a fish from the Ordovician period is the armored ostracoder. The descendants of these armored fish that exist today include lampreys and hagfish. The echinoderm phylum reached its highest level of diversity, with up to 20 classes existing during the Ordovician period. Crinoids, commonly known as sea lilies, were the most abundant species at the time. They resembled feathered plants, attaching themselves to the ocean floor with their arms, while their tentacles floated gently in the water. On land, life during the Ordovician was primarily dominated by non-vascular plants such as mosses and ferns, which lacked a vascular system to transport water and nutrients. This can be considered the first experiment in the evolution of terrestrial plants, a positive yet incomplete step toward life on land. Notably, the presence of green microalgae and fungi played a significant role. These simple life forms created the first lichen layer on the Earth's surface. These natural allies can be seen as the first architects of terrestrial life, laying the groundwork for biodiversity and complexity in later periods. Although these early terrestrial life forms seem modest compared to the richness and diversity of modern ecosystems, they paved the way for a new era of life on land, an era where plants and animals began to dominate and adapt to this new and challenging environment. Thus, the Ordovician period not only marked a significant evolutionary milestone underwater, but also set the stage for the development and diversification of more advanced life forms that would eventually thrive in environments beyond the ocean's reach. The End-Ordovician and early Silurian extinction was a significant event in geological history, occurring around 445.2 to 440.8 million years ago. This event wiped out an estimated 85% of the species living during the Ordovician period. In terms of severity, measured by the proportion of marine animal families affected, this extinction ranks second only to the Permian-Triassic extinction about 251 million years ago. As such, this extinction was almost twice as severe as the End Cretaceous extinction, which occurred around 66 million years ago and is famous for ending the existence of the dinosaurs. One of the main causes is thought to be the movement of the Gondwana continent toward Earth's South Pole. This shift created large ice sheets, leading to a drop in sea levels and changes in ocean currents. As a result, unique and diverse habitats like inland seas were destroyed, reducing the richness of species living in them. Additionally, the reduction of CO2 in the atmosphere due to the erosion of silicate rocks may have caused global cooling, which could have contributed to the extinction by altering the composition of water and habitats. As the Earth cooled, sea levels dropped, causing large inland seas on the continents to dry up. Glaciation trapped water away from the oceans, but interglacial periods melted the ice. This created a cycle of sea levels dropping and rising repeatedly over time. The shallow, expansive, and near-continental seas of the Ordovician period receded, killing off many species. When they returned, they brought back those species, but with less diversity. Then, As glaciers came again, the seas receded once more, killing the species and reducing biodiversity further. And that is the story of the formation and end of the Ordovician period, spanning millions of years with remarkable geological and biological changes. The Ordovician period not only marked the emergence and development of many important groups of organisms, but it also laid the foundation for our understanding of extinction processes and the recovery of ecosystems. It serves as a bridge between the Earth's ancient past and its promising future, while also ushering in a new era for more advanced animals, the vertebrates. Now, if you enjoyed this content, don't forget to hit the like button, subscribe to our channel, and click the notification bell so you don't miss any upcoming videos. Additionally, you can support us directly through the information provided in the description. Thank you for listening, and we'll see you next time